This is our introduction to Chapter 26. I'm going to preface this by saying in Chapter 26 he spends a lot of time on details that I think are not important. And when I say that, I don't mean they are not important details if you are to continue on with this. So, for example, I know some of you will be doing a circuit analysis class soon after this. And some of the things that are done in this chapter and succeeding chapters, I believe, some of the things that are done in this chapter are kind of very similar to what you'll be doing in that class. But I think it's more detailed than we need to understand the principles. So, for example, the very first section in Chapter 26, he starts talking about the internal resistance of a battery. And yes, you can look at this and you can do the calculation, but you don't learn anything new about resistance by doing that. We should read it and at least be aware of it, but the actual influence on how a circuit performs is so easy to incorporate. You just throw in another resistor, and that's what this chapter is about, is kind of what happens when you throw in another resistor, and a little bit more than that. So you can deal with another resistor whether it happens to be inside a battery or outside a battery. So do you really need to know that a battery has an internal resistance? I don't know. So there will be that and some other things that I will not be covering in detail. But on the other hand, I do think that there's something that's not presented very clearly here. And it's not done very explicitly. So I'm just going to, like I did this in class already, but this is what you need to do when you are presented with a circuit. This is what the things you need to remember. For our purposes, we will consider that a battery, remember this is the symbol for a battery, with this being the positive side, this being the negative side, and traditionally we just call this has a voltage of V and this has a voltage of 0. But remember, the only thing that matters is the potential difference. Another name for what a battery provides is called electromotive force. It's just a historical name. It's usually written like that. Like I said, the only reason I think that electromotive force is a nice name to have is because then you have Pi's law, which we did discuss already, which is the power is equal to the current times the electromotive force, which you can, if you remember it as P equals IV, you're fine, right? So I don't know. So, but electromotive force is just another word for voltage. That's all the only way we're going to consider it. Okay, so now we've got some circuit going out here. We've got some resistance. Let's say we got a resistance like this. Let's make it interesting and go like this. Okay, so I'm not going to analyze this in detail right now, but what I am going to do is remind you of the process we go through. What we do is we say, which remember, this goes back to the very, very first principles from the very first lab we did, from the very first, as soon as we started talking about this charge. This is a conductor. If you just see a line like this, it's a conductor. Conductor, what do we know about it? Charges are free to move. What do we know about a battery? If there is a potential difference, there is an electric field. If there is an electric field, there is a force on charges. If there is force on charges and there is a conductor, the conductor charges are free to move, therefore they are going to move. Okay, so that's item number 1. Charges are going to move. Item number 2, just to remember this, is that we consider this battery as a source that will always maintain this voltage. And so it is going to do whatever is necessary to create this voltage. Well, what that means is as some of the charge from here disappears and goes up here, in other words, repels one another and goes up here, it's going to make new charge until there is just as much of force pushing back as there is pushing this way. Well, what does that mean? That means that the potential here, you probably can't see that, the potential anywhere here on this wire is equal to V. Until you get to a component, the potential is equal to V. All right, Same thing on the other side. If this is 0, then this is 0 here, this is 0. So item number 1, conductors, any place where you just have a conductor, that is at the same potential. And just of interest, here and here, that's equally true, but it's not true it's not the same value that you get over here. It just is the same anywhere on this stretch where there is no other component. That's just a little tidbit. Okay, that's the first thing. Second thing, V equals IR, Ohm's law. That's the next thing you need to know. The third thing you need to know is it's actually there are two different ways of thinking of the same thing. They both go by names called Kirchhoffs Law, and one of them basically says, however much current you have coming in here, that is, however much moving charge, however much charge you have moving right to this point, the charge that moves this way and the charge that moves this way must total up to that same amount. And the analogy I use is that stream in the woods. You're walking along in the stream of the woods. If it splits into two parts, then one part, the sum of those two parts can only have come from the one stream that goes into them. Or vice versa. If you have two streams that are coming together and creating a bigger stream, then the amount of current in that bigger stream must equal the amount of current in the other two streams coming into it. So that's called Kirchhoff. That's one of Kirchhoff's laws. It's Kirchhoff. I actually don't know what the formal name for it is. Kirchhoff's current law? I don't know. The other Kirchhoff's law here is the same as the conservation of energy. You will recall that Q times V is equal to the energy. You will also recall that it doesn't matter which direction we go when we're talking about potential energy. Remember the top of the hill, it doesn't matter if we go straight down the hill or whether we go around in circles, which means if I start here and I go all the way here, back to here, I'm going to have a certain potential difference as I go through there. That potential difference must equal the potential difference that happens if I go in this direction. Actually, it must be the negative of it. So yeah, I think that makes sense to you all. Oh, and if I go here, if I start here and I go out here and go all the way through here, all the way through here, all the way back to here, all the way back to here, that potential difference must also equal the potential difference that I have here. So that's it. Those are the 4 things you need to pay attention to, 4.5, I guess, with the starting one being that our battery will always work to provide V no matter what. So if you see a battery, it's providing a voltage V. That's number 1. Number 2, the potential will always be the same on any conductor. Any length where there's only a conductor, the potential will always be the same. Number 3 is Ohm's law. Number 4 is the Kirchhoff's current law, junction rule maybe? Maybe that's it, Kirchhoff's junction rule, where the current coming into a junction must equal the current going out and vice versa. And number 4, that the potential going one way around a path must be equal to the potential going another way around the path, with the addition of a minus sign where necessary, where you're going in the opposite direction, okay? And that's it. Everything else is just how we're going to apply that. Okay, that's the introduction.